are from MIT Manipal. We are participating in TI Analog Design Contest 2012-2013, and we are Team D. The problem statement for our team is first problem is a function generator which has a non-inverting integrator in loop with Smith trigger circuit. The second op-amp is in positive regenerative feedback. So we are basically getting two outputs. One is a triangular output and the other is a square output. Okay, so two op-amps have been used. In the ASLV kit we have used 4A and 4B op-amps. This is the circuit for the function generator. Okay, now I'll show you the implementation in ASLV kit. This is basically the two op-amps, 4A and 4B. 4A's connections are this. We have used the resistors like for R21, R24P. This is the circuit. This is the 4A op-amp and 4B. These are the connections, the pin diagram. Are U4P2, U4P3 and U4P1. Basically this op-amp which we are connected, which we have connected along with the other op-amp U4B. I'll show you the connection in circuit. This is the ASLV kit which we are using. This is the power supply which we have connected to a digital IC trainer with 12 volt supply. Plus 12, 0 and minus 12. The two op-amps which we are using are here, 4A and 4B. These are the connections. Like initially first connection is done from the resistance to the op-amp. U4P2 to R16. This all are connected. R16 is grounded over here. Then we have connected R21 to R24P. This is the circuit which we have simulated in PSpice OrCAD Capture. The first op-amp and the second op-amp. This is the Smith trigger circuit, and this is for the positive regenerative feedback. Okay, so simulating it gives this result. This is the square output, the final output, and this is the triangular wave, which is the first op-amp output. The green one is the triangular wave output and the red one is the square voltage output. Circuit we have used 4A and 4B op-amps. This is the connection in the ASLV kit. The power supply we derive it from plus 12 volt digital IC trainer kit, 12 volt, minus 12 and 0 volt. This is the connection. We have connected it here. Now here mainly the resistance is 1K, 2.2K and capacitor 1 microfarad has been used. So we have used C17P for op-amp 4A, which is 1 microfarad, R21P, R23P, R16P and R19P for 4A op-amps, which are 1K and 2.2K resistance. And for the 4B op-amp we have used R24P, R26P. Yeah, that's it. It's 1K and 2.2K. This is the feedback. R21 is connected to R2.4, 2.2K, which is R24P. Okay. So basically, we have then used a digital CRO to get the output waveforms. These are the two output waveforms. The square wave is connected to the channel 1 input of the digital CRO, and the triangular waveform output is connected to the channel 2 of the digital CRO. These are the two connections, and these are the two outputs. The square wave output, which we are getting around 16.6 volts peak to peak, and for the frequency we got 1.085 kilohertz. The triangular wave, it's 11.426 peak to peak, and frequency is 1.085 kilohertz. Move on to our second circuit, which is basically a voltage controlled oscillator. The function generator, the previous circuit which we had, we just add a multiplier which is MPY634 kp to the feedback loop so that we get a voltage controlled oscillator, and the two inputs are One is the output of the second op-amp, the square wave output which you are getting from the function generator, you give as input to the multiplier, and the second input is a DC voltage which will vary in steps. And the output is connected to the first op-amp. We basically see the functions of a voltage controlled oscillator. Like as we vary the input voltage VC, we see the change in the frequency of the output waveform. But minute change in voltage, we get a change in frequency. So as we vary the VC voltage in steps, here we'll vary the voltage up to 10 volt near about. So and we'll see the frequency output variations. Basically, circuit, we change only the two connections. The feedback which was earlier connected to R21 to R24P, now we have changed it. This is the multiplier which we have used, MPY634KP, and for the multiplier basically the connections are this. Input 1 is connected to the 1 pin, input 2 is connected to the 6th pin, and 2, 7, 10th pin are shorted. Output is taken tapped from the 11 and 12th pin which is externally shorted. So the multiplier which we have used is this one. Here we have shorted 2, 7th and 10th pin, and the supply of the kit we have connected to the same digital IC trainer kit, plus 12, minus 12 and 0 volt. And the two inputs which we are given, one is this DC supply which is the VC as shown in the circuit, control voltage. We have connected this to the input 1, and the other input is from R24P of the 4B op-amp which we have connected to the multiplier. Basically it acts as the multiplier is placed in the feedback loop, and the output of the multiplier is connected to the R21P of the 4A op-amp. We will see how the circuit works. Okay, the two outputs are connected to the digital CRO. First the triangular, and the channel 1 is connected to the square wave output, and the channel 2 is connected to the triangular wave output. So initially we have kept DC voltage to be 1, and we can see the frequency is 156.7 Hz. Now as we increase the voltage to around 2.7, the frequency also increases. It comes to about 318 or 320 Hz. Now increasing the voltage shows a increase in the frequency. We can see for 3.8 volts it's coming around 444. For 5 volts it has come around 581 Hz. So basically as we decrease the voltage, the frequency decreases, and as we increase the voltage, the frequency increases. We can increase it like up to 7.6 volt, and here we can see the frequency is increasing, and it's about 1 kHz at 8.8 volt. So it's doing the function of a voltage controlled oscillator, and the peak to peak voltage for both the circuit remains near about constant. The output voltage, square output voltage, peak to peak voltage is same, and as well as the triangular waveform, peak to peak voltage is around 13.814, and for the square wave it is 20.2 volt, but the frequency varies as we increase the control voltage.